Well, I think the trouble with string theory is that there isn't any connection with observations. As far as I'm probably taking too strong a view here, but the mathematics, I mean, it's largely driven by the mathematics as far as I know, which is in itself is not an objection as far as I'm concerned. A lot of what I do is driven by the mathematics. But the trouble with string theory is it's supposed to be a theory of the way the world operates. And if the number of dimensions of space is just wrong, I can't take.
In the field of physics, where the mysteries of the universe are uncovered and our understanding is constantly challenged, Sir Roger Penrose is a significant figure. He's well known for his contributions to cosmology, black hole theory, and mathematical physics. However, what makes him stand out in the scientific community are his ideas about dark matter and the widely accepted string theory. Join us as we delve into Sir Roger Penrose's thought-provoking ideas, suggesting that string theory is wrong and that dark matter might not be exactly what it appears to be. String theory is one of the most debated concepts in modern theoretical physics. This theory attempts to reconcile two fundamental 20th century physics theories, quantum mechanics and general relativity. It suggests that instead of particles being point-like, they are tiny strings that vibrate, playing a fundamental role in shaping our universe. The core idea of string theory arises from the recognition that quantum mechanics, which explains particle behavior at the atomic and subatomic scale, and general relativity, which deals with gravity on cosmic scales, are successful in their domains but clash when combined. This leads to deep paradoxes and mathematical inconsistencies. String theory aims to harmonize these conflicting theories, providing a unified understanding of the universe. String theory's roots can be traced back to the late 1960s through the pioneering work of scientists like Leonard Susskind and Holger Bech-Nielsen. It gained prominence with the development of the Veneziano amplitude by Leonard Susskind and Gabriel Veneziano, forming the foundation for string theory and leading to the first string theory model known as bosonic string theory. A notable feature of string theory is its introduction of a new concept of scale. Instead of viewing particles as dimensionless points, as traditional quantum field theory does, string theory proposes that they are extremely small vibrating strings. These strings can vibrate at various frequencies and modes, much like musical strings producing different tones. Each vibrational mode corresponds to a different particle. This concept elegantly addresses issues related to particle mass. While the standard model introduces the Higgs mechanism to give particles mass, string theory naturally attributes mass to particles based on the energy of string vibrations. Different vibrational modes of a string correspond to particles with varying masses. This interconnectedness of particles through string vibrations is a key aspect of string theory. String theory also suggests the existence of a minimum length scale in the universe, known as the Planck length, which is about 1.6 x 10 circumflex 35 meters. This scale represents the smallest distance possible in our universe and becomes crucial when addressing questions related to singularities, like those found at the centers of black holes or the moment of the Big Bang. String theory proposes that at the Planck scale, the fabric of space and time itself might have a different structure than what we typically perceive. An essential aspect of string theory is the unification of forces. In the standard model, there are four fundamental forces: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. String theory aims to unify these forces within a single mathematical framework. It suggests that the various vibrational modes of strings correspond not only to different particles, but also to different forces, potentially describing all forces as various manifestations of a single underlying principle. The idea of unifying forces is closely connected to supersymmetry, a fundamental part of string theory. Supersymmetry suggests that for every known particle fermion, there's a corresponding superpartner boson, and vice versa. While experiments haven't observed supersymmetry yet, it's essential in string theory as it stabilizes the theory and could potentially resolve some issues in the standard model. Nevertheless, it's crucial to acknowledge that string theory faces its fair share of challenges and controversies. One of the primary criticisms revolves around the lack of empirical evidence. Despite being an active field of research for many decades, string theory hasn't produced concrete, testable predictions that could be experimentally confirmed. This absence of experimental validation has prompted skepticism from physicists, including the Nobel laureate Roger Penrose, regarding the scientific credibility of string theory. Roger Penrose, a distinguished theoretical physicist and mathematician, is renowned for his significant contributions to various areas of physics, particularly in the realms of black holes and cosmology. While his work has been groundbreaking and recognized with awards, Penrose has also expressed critical views about string theory, questioning its scientific legitimacy. You see, a central aspect of the scientific method relies on empirical evidence to either validate or invalidate a theory. Penrose's skepticism about string theory stems from its limited experimental support. Unlike firmly established physics theories like quantum electrodynamics or general relativity, string theory hasn't produced testable predictions that can be confirmed through experiments. This absence of empirical verification raises questions about string theory's scientific status. Despite being around for decades, string theory, while showing intriguing mathematical developments, still faces a substantial challenge due to its inability to make predictions that can be tested in the laboratory or through astronomical observations. Penrose's standpoint is that a scientific theory should have the capacity to make predictions and stand up to empirical scrutiny. Without this validation, string theory's classification as a scientific theory is brought into doubt. This concern aligns with the broader scientific community's expectations concerning the falsifiability and empirical validation of theories. Another issue with string theory is its reputation for mathematical complexity. It often deals with a higher number of dimensions, typically 10 or 11, which goes significantly beyond our familiar 3 spatial dimensions and 1 time dimension. The introduction of additional dimensions beyond our everyday experience is a fundamental feature of string theory, necessary to accommodate the vibrations of strings in a manner that unifies forces and particles. However, the intricacy of string theory presents challenges when it comes to comprehending and working with the theory. Penrose has contended that the mathematical complexity and abstract nature of string theory make it less intuitive and, in his perspective, less appealing as a fundamental theory of the universe. Historical principles of simplicity and elegance have often guided the development of successful physical theories, and Penrose's viewpoint underscores the unconventional nature of string theory in this regard. Penrose has also questioned the internal consistency and predictive capacity of string theory. While string theory aims for unification, the abundance of potential string configurations and the diverse options for Calabi-Yau shapes used to compactify extra dimensions have led to a proliferation of potential solutions. This multitude of solutions has made it challenging to identify unique predictions for the theory, further complicating its experimental testability. Additionally, the concept of supersymmetry, which plays a critical role in string theory, has yet to find empirical confirmation. Supersymmetric particles, or superpartners, have not been observed in experiments, sparking debates within the scientific community about whether supersymmetry represents an authentic aspect of the universe or remains a theoretical construct. In this context, Penrose's criticism underscores the necessity for a theory to possess internal consistency and the ability to generate distinct predictions that can be tested against empirical observations. Penrose's critique extends beyond scientific considerations into the realms of aesthetics and philosophy. He has voiced the view that string theory lacks the elegance and beauty typically associated with successful physical theories. He places significant emphasis on the aesthetic appeal of a theory as an indicator of its potential to reflect the true nature of the universe. Furthermore, Penrose's contributions to cosmology have led him to develop alternative models, such as conformal cyclic cosmology, which offer different perspectives on the universe's origin and structure. These alternative concepts reflect his commitment to exploring novel ideas that may better align with his philosophical and aesthetic preferences. Let's now delve into why Sir Roger Penrose, a renowned physicist and mathematician, questions the existence of dark matter, despite its widespread acknowledgement in the scientific community. Penrose's doubts about dark matter originate from his inclination towards an alternative explanation for the gravitational oddities observed in galaxies and galactic clusters. Instead of proposing the presence of invisible and undiscovered dark matter, Penrose offers a different perspective on understanding these anomalies. His alternative theory, referred to as conformal cyclic cosmology, suggests that the gravitational impacts attributed to dark matter might actually be an outcome of the universe's inherent structure and the expansion of space itself. In the CCC framework, Penrose challenges the notion of dark matter by suggesting that the universe's expansion results in the gradual transformation of massive particles into massless particles over incredibly long time frames. According to Penrose, this transformation can contribute to the gravitational effects often linked to dark matter. Essentially, he argues that dark matter might not be necessary, as these effects could be explained by the behavior of particles as they lose mass over time. Penrose's unconventional stance on dark matter reflects his strong preference for simple and elegant scientific theories. He asserts that his CCC model provides a more straightforward and aesthetically pleasing explanation for phenomena commonly attributed to dark matter, aligning with his broader philosophical and aesthetic sensibilities. So what are your thoughts on Roger Penrose's ideas? Do you support the idea that dark matter doesn't exist? Tell us in the comment section.
Yeah.